So I'm here this morning with Dr. Rita Colwell, who is a distinguished university professor at the University of Maryland at College Park and at Johns Hopkins University Bloomberg School of Public Health. She's also a former director of the National Science Foundation. She did that from 98 to 2004. And she is a huge advocate for K through 12 science and math education, and also in increasing the participation of women and minorities in science and engineering, for sure. I know you're passionate about that. So we'll start with your present research. You obviously have a huge CV of research projects, but what is grabbing your interest right now? What's your primary focus now, and what are your goals with that work?
Really, the interest is the intercalation, the connection between the environment and human health. The ability with computational capabilities that we have to be able to integrate the kind of data that we're gathering concerning the environment, and at the same time, the effect that it has on human health. I think up until recent years, physicians have focused, quite rightly, on epidemiology between individuals, person-to-person transmission of infections. But we've learned in the last few years that the reservoir of so many of the infectious agents is the environment. And the direct transmission from the environment to humans is a critical understanding that we need to develop. This information then allows us to be able to predict potential epidemics and not leave us sort of flat-footed the way we were with COVID-19, but to have the capacity, the ability to provide an early warning system. And the fact that we now know, because of the intense studies of COVID-19, that from the first point of infection, you may have 5 to 7 or possibly even 10 days before cases appear. And so that provides an opportunity to be prepared, to begin to consider, perhaps too early to consider vaccines, but at least to be prepared for the outcome. Now, we've been able to do this, when I say we, my students and I, for cholera. At the present time, we're working with the British Aid Agency and UNICEF to predict the risk of cholera in a month in advance for Yemen. And this allows then the medical component of the aid agency to be prepared. They can go to specifically those sites in Yemen where the highest risk of cholera will be. And this, of course, saves money, saves time, saves lives.
Does cholera change and morph so much that you wouldn't be able to detect it, or is the underlying organism the same, so it's easy to?
It's a concatenation of environmental parameters. It's a waterborne disease. So the combination of air temperature, water temperatures, the presence of plankton, because what we had shown some 30 years ago was that the cholera bacterium is actually hosted by the copepod, which is a component of the zooplankton in aquatic systems. Now, that wasn't accepted readily. In fact, it was really resisted, quite unpleasantly resisted by the medical community. But now, of course, it's in textbooks. And it's understood that the host is the copepod predominantly. Other components can, small numbers, carry the Vibrio cholerae, the causative agent of cholera. But essentially, the copepod is its natural host. And in an aquatic system, in the spring months, first there's a phytoplankton bloom because sunlight creates a bolster for the phytoplankton community, and then the zooplankton feeds on it, so that it becomes dominant. And we were able to show in places like Bangladesh, where the villagers take water directly from the ponds, the streams, the aquatic area, that in the spring they will have, even today, increases, not such a major epidemic as in the past, but increase in the spring, and then another major epidemic in the fall, correlated very, very tightly to the plankton populations. So by deciphering the interactions between the environment, we come up with the prediction. And then with intensive mathematical computation and building models, we can predict.
Okay, so you're looking, it's like you said, you're looking at the environment, you're looking for sort of all the factors that are the perfect environment, the perfect host for this cholera to come out.
And we're intercalating and introducing now the kinds of what I guess you would call a standard epidemiological medical approach. That is, we're now looking at immunity, previous infections, the possibility of variations. And we have found in our molecular genetic work that we do, in addition to the mathematical modeling, microbiome sequencing, and determining community structure, we now know that their capacity for the bacterium to transfer genes, about 80% of its genes can be transferred, not all at once, but they're transferable. And in fact, the specific characteristics, serotype, is coded by a set of genes that are transferred. So that's another really big problem. So the fact that the genes for the serotype can be transferred indicates that you can build a vaccine against a strain that appears now, but the genes for the serotype may transfer. And it's long been known that the toxin gene is transferred by a filamentous phage. So when you've got this kind of mobility within a population of the cholera bacteria, you have kind of a mix and match situation.
Yeah, so the more projections and forecasting you can do, the better.
Exactly.
Try to help them prepare.
And this is, of course, what's happening with COVID-19.
Right.
Mutations and variants that are selected and following the evolutionary path of life on this planet.
Yes, that's kind of how that works. Mother Nature is definitely in charge, no matter what we like to think. So, as part of the expeditions community, how do you see your work enhancing? I mean, it's kind of obvious to me, but from your perspective, how do you sort of fit into the overall goals of the expeditions project?
I'm very excited about the work that we're doing collectively because it brings in a wonderful mix of scientific, engineering, mathematical, environmental, molecular, and medical expertise. And we now have the mathematical capability, even with big data and analyzing, to be able to pull the connections and the correlations out of all this. And with all these good minds focused on interpreting, reassessing, rearranging, and reorganizing the data and the analysis, the analytics, this is an extraordinary opportunity. And working with the team is great fun. I enjoy it immensely.
Yes, it's a very exciting, enthusiastic team. Even though everyone is overworked with the happenings of the last year, I feel like there's still a lot of energy and excitement and enthusiasm that we can get in front of the next one. We really can.
Because of the insights, it's the kind of aha that comes with the discussion, the lectures that are given, the meetings and the discussion. You get a new idea that you can pursue, and that's, of course, the benefit.
Absolutely. So how did you get into this business?
How did I get into
cholera research, into all of this in general? Like how did you get here?
Well, that's a kind of zigzag course. It was not a straight downfield run. I started out heading to medical school, and at Purdue University, where I attended as an undergraduate, I in the spring of my senior year, I met my husband to be. We got married. It was a whirlwind romance. We were married within 2 months, and it was a 62 very, very happy marriage. So 62-year very happy marriage, and I lost him 2 years ago. So I miss him terribly, but we worked together over the years, raising two terrific children. We got our PhDs together, and the interesting thing was that in that senior semester year, I was accepted to medical school. I was heading to medical school, met Jack, we got married. I went to the department chairman and said, look, he's been here, he's a returning veteran from serving in the Army, and he will lose a year if we move on. So why don't I stay, get a master's? He gets his master's, then we'll move on. I'll go on to med school. And the med school agreed to keep my appointment open. But the department chairman said, we don't waste fellowships on women. So I went to my undergraduate advisor, Dr. Alan Burdick, who was a geneticist. He said, oh, well, he said, their loss is my gain. He said, I have a research assistantship. You can do a master's in genetics. So that's what I did. And it turned out to be the most fortuitous because it wasn't that much later than the discovery of the DNA helix and the whole molecular revolution. And so my husband got accepted as a graduate student at the University of Washington. I applied to medical school. I was accepted, but got another letter saying, you have to be a resident for a year and then you can go to medical school. So I ended up going into microbiology. So it's been a very zigzaggy course, and I finally became probably the first officially trained marine microbiologist in the US.
Wow.
And Vibrios are very common in the aquatic environment. I made the discovery that Vibrio cholerae is an aquatic bacterium and that it can never be eradicated. It can be well controlled, as we know,
Right.
in the US by safe drinking water. So that's how I arrived where I am.
So what is in all your research, because I know you've done field work all over the world. I know you have. But what is the most interesting or strangest or sort of out of body, research experience you had where you're, I don't know, standing in the middle of Angkor Wat thinking, I can't believe I'm here, or whatever?
The very best was when I was director of NSF. The director of NSF is essentially the czar or czarina, in my case, of the Antarctic. We run the Antarctic Science Station, and you're essentially a sort of ambassador for the Antarctic. And so going to the South Pole was, for me, the greatest experience of all. It's almost a religious experience to fly into that pure white continent that with the volcanic mountain that's still a volcano emitting steam, and yet around is totally ice and snow. So that was a fascinating experience. I really found that to be probably the most dramatic of my work. And I was there at least 9 times. So I flew many times because as director, you generally invite congressional delegation to go down to see how the work and the science is done, which is very important to do because then they have to spend time there. You don't just fly in and fly out. It takes a good day or so to get there, and then 2 or 3 days to be able to see what's going on. So you have an opportunity for congressional delegations to really spend time with scientists and to convert them.
I have a question about Antarctica for you. I have a friend who worked at SeaWorld, and so I got to go behind the scenes in the penguin encounter. Those penguins are stinky. They're so
They're not very nice. They're cute, but they're not very
they're
nice.
not very nice. Just remember how stinky, and they said that's why the penguin exhibits are all behind thick glass because they're so stinky.
Well, they also are pretty ferocious. They fight. I mean, they don't look as though they can be damaging, but when they start snapping at you, you want to get out of their way. However, they are fun. I think the most amusing episode I had in Antarctica was visiting the penguin rookery. And it's like being at a Washington cocktail party because all of these penguins are fascinated by you as an outsider. And so they all stand around kind of gobbling to each other, talking to each other. And you're wondering what kind of chit chat they're actually saying about these strange beings that have showed up. But they look like little folks in their tuxedos.
Sure. Yeah, I would not have thought of them as being mean or vicious, because we only see like the cute little movie penguins, right?
Well, they're very protective of their young, as they should.
Sure. Yeah, I mean, we're scary to them, I'm sure.
And there are birds, skuas, that go after their young and their eggs. And it's quite interesting to see one of these skua flying in, and those penguins go after it very, very energetically. And if they catch one, it's the end for that.
That is a great memory for an odd place your science has taken you. I couldn't even imagine. So now, looking to the next generation, what advice would you give to some students who say, I want to be Rita Colwell. I want to do the things that she's done. I want to be involved in this at this level, in this research.
Do what you like, do what you love. Work on that which really excites you and interests you. And I think too many youngsters today look to see what will get them a job. And that's dangerous because the jobs today are not the jobs tomorrow. In fact, when you graduate from college, essentially half of what you have learned at the time of graduation is already obsolete. So you have to be a perpetual student, learner. Therefore, if you're doing what you really love, then you will keep up and you will be at the forefront, and it'll be very exciting. The other advice, particularly for women, is get yourself a posse, because you'll come up against various kinds of interruptions, interferences, inhibitions to what you would like to do. And if you have friends, particularly for young women who are just starting let's say a career as an assistant professor, get a lunch group together of other women in other departments as well as your own. And you'll find that a lot of the pushbacks and a lot of the interferences and even the harassment will not be unique to you, but shared. And that makes it a whole lot easier to tolerate and to overcome. And this holds, I think, for men as well, but particularly for women.
Yeah, and particularly in science, math, engineering fields.
Exactly.
Yeah. Thank you so much.